So we've seen it before when the end of the game comes, and be it football or soccer or rugby, you have a defenseman who just can't seem to make it to the ball in time for a contested pass or contested shot. And it looks like they're just dragging their feet, and their legs are made out of lead. So this is what we want to identify. This is what we're looking into for this project, is identifying fatigue without using their biometric data. So I'll introduce myself. My name is Aaron Pearson. I recently graduated from Simon Fraser University with a Bachelor's of Science. I hold a major in kinesiology and a minor in statistics. And for 3+ years now, I've been working in the quantitative exercise biology lab at SFU, where I was researching the interplay between cardiovascular fitness and metabolic thresholds, as well as fatigue and fitness levels and how they can or do correlate to injury. Overall, for this project, we're looking to identify fatigue by bridging exercise physiology with data analytics and statistical modeling. So there were a few questions that we looked to answer, and unfortunately we didn't get to answer all of them. But what we want to know is, for your soccer player of choice, can we quantify their fatigue levels? Can we identify their changes in behavior using the estimated fatigue levels? And can we then estimate how much longer these players have at the current pace of play before they become fatigued? We can then apply this to decreasing injury risk, improving coaching decisions by telling coaches who is tired or who may become tired, by helping strength coaches better prepare their athletes, and better understanding team matchups or demands from upcoming teams to know how to better prepare. Do they play kick and run? Well, can some of our players, this player in particular who you're thinking of, keep up with that pace of play and the demands from that team? So even though soccer is the most popular sport in the world, well, what do we really know about it? So soccer is made up of a lot of intermittent bouts of high velocity runs that last about half a second each. Now, these runs are actually more well defined as high acceleration runs that last about half a second, because these are what these accelerations or these runs are what define who wins a contested pass. We also know that carbohydrates are the main fuel source for soccer players, especially at the end of games where we've seen that they are low on it. And carbohydrates are what fuel the 1,000 to 2,000 distinct movements that players make throughout the game. Finally, we know that our soccer player here will have less high-speed running at the end of each half, significantly less in the last 15 minutes of the second half. And with coaches making proper substitutions, this soccer player of choice here won't be able to keep up with a substitute, because the substitute has fresh legs and ours does not. So overall, it all depends on energy, or part of it relies on energy rather. But there's an issue with this image that we've seen time and time again. It just doesn't take into account effort, right? Our soccer player here is assumed to run for 300 seconds at an all-out pace, and then this is our contribution of total energy. But rather, I prefer this image here, where we see that where this line is, to the right of it, our vigorous and maximal efforts rely heavily on carbohydrates and far less on fats. And on the left-hand side, which is our walking and jogging paces, well, it's a good mixture between the two. And this is what fuels our accelerations, and this is what fuels the end-of-game efforts for those who need to make our high-speed or high acceleration runs. We also had to define what fatigue is for our players. So fatigue for this project was defined as the inability to produce or sustain force output for a given task at the required level. Vague and open to interpretation, and that was done purposefully. And that's done purposefully because we have two types of fatigue. We have central fatigue and we have peripheral fatigue. Central fatigue stems from the brain, so it's usually or colloquially understood to be mental fatigue. And it's theorized to be a protective mechanism. So what do I mean? Well, when we're active, our core temperature increases. This forces blood to the skin to help heat dissipate. Well, when our core temperature rises too much, the brain senses this and decreases our neural drive, or how much work we're doing or can do to draw blood back into the torso or the thorax where the organs are, because it's more important to save our organs for survival than it is to dissipate heat at that point. And we're going to decrease our core temperature by just doing less activity. It could also be, and this is another theory, that we just don't like pain. So we have pain, in our muscles from lactic acid buildup and all these metabolites that build up, that the brain receives these pain signals, and we decrease neural drive because we just don't want to be in pain. We don't want to be working at a pace that is painful for us. We also have peripheral fatigue, which is a lot more intuitive. So it's the stuff that happens inside the muscle cell. So this comes mainly from two parts, essentially. It's the fact that we might not have enough energy or quick energy to keep up a certain pace, or it could be the byproducts of using this energy and making more energy, which are called metabolites. So stuff like hydrogen ions and carbon dioxide, well, they create an acidic environment which interfere with enzymes. Inorganic phosphate can interfere with just overall muscle contraction at the myosin actin level, and magnesium interferes with calcium release, which is calcium is the most important ion for muscle contraction. Without calcium, we cannot contract, and if there's too much calcium, well, we stay rigid and we can't relax. Finally, dehydration, which is a huge factor in sports, especially soccer, plays a huge role. Dehydration helps a lot of functions or bodily functions to occur, but on top of that, water actually helps bring carbohydrates, brings blood glucose into the cell. So if we lack water, we can't bring more energy into the cell. We become less efficient at breaking it down because of our metabolites, and we just can't sustain the force required for the game. So in summary, I've built this table, but what we really need to take away from this is that we have a decrease in force production. More muscle units or muscle fibers are recruited, forcing the body to use more energy to perform the same actions, leading to just an overall decrease in performance and athletic ability. On top of all this, we have slower response times, leading to more potential mistakes to be made on the field. So what do we need to know about our soccer player? Well, we need to know his fitness levels, and we need to know his overall ability. So estimating his fitness levels will come from the critical power model. The critical power is defined as the power output that can be sustained indefinitely. It's defined as being at or just above second threshold. So it's defined as the point at which we're using energy just as much as we are it's being reconstituted or remade, essentially. Critical velocity is the outward expression of it, so it's essentially the velocity we can maintain indefinitely under the same definition, using energy at the same rate as reconstituting it. It's very sport specific and muscle specific, and to understand our fitness levels for the soccer player, we have to first compute this from our tracking data. We then also have to incorporate the W prime balance model. So this is essentially how much anaerobic capacity does our soccer player have. If he runs out of anaerobic energy or anaerobic capacity, he can't he can't have these big bursts of speed or acceleration, especially at the end of the game. So this model not only estimates how much anaerobic capacity they have, but how quickly it's being used and how quickly it's being reconstituted. So from both of these, we look to apply it. So here is our theoretical model of what we can make. So we have our max mean velocity on the left, and our asymptote that's made here is our critical velocity. So in this case, it's approximately 2.5 meters per second. And we can calculate d prime, which is our outward expression of w prime, from this graph, but we're not going to get into it too much here. From this information, we can actually build from tracking data something that looks more like this. And this is from actual tracking data from somebody who's had about 30 sessions. So yes, we could use more data to make it a smoother fit, but we have this curve that occurs, and when we fit an asymptote to it, we can find his critical velocity here, and it's somewhere around 2. It doesn't really matter where it sits for this example, but we know that if he's out of anaerobic capacity, he can only reach about 2 meters per second, which is really like a slow to moderate jog. And he won't be able to keep up with the pace of play, or he won't be able to keep up with for contested passes. So moving forward from there, we can build something that looks like this. This is his velocity and his power output, it should be velocity and d prime. And we see that when we put our asymptote in here at about 2 meters per second, that any velocity above it, so the light gray line above it, he will actually be using his anaerobic capacity, his d prime. And anything below it, we see d prime increase again. And that's what we're trying to build here, is real-time feedback for coaches to see how close to empty our soccer player is. We can see at about 45, 50 minutes of gameplay here that they reach 0, and they're more of a burden to the team. If they can't contest passes or they can't make these large runs, then helpful or useful. To achieve all of this, we had to do a few things. First and foremost, we had to get GPS data and IMU data. We had to understand how we're going to set inclusion criteria to extract these runs. So what we did was we wanted runs that are fast enough or hard enough acceleration and somewhat linear to compare to each other, so we can then analyze them and hopefully extract parameters, cluster them, analyze them, and then move forward from there to understand which parameters are best seen at different times of play. So what are the results? Well, here we have an entire session. This is one session for one player. We identify the runs, and then we extracted the runs, and we identify about 100 to 200 instances per game that are at least half a second long. Some projections here were then smoothed because something like a deke or the ball being pulled back for 0.1, 0.2 seconds before moving forward to get past the defender, we then smoothed them because we felt like it wasn't fair to compare a broken line to other broken lines, essentially. So what do we find? Well, we pulled out all these parameters. Some of them are still being worked on. The italicized ones are. But we found that we have 3 clusters of runs that we can compare behavioral changes to. One's in the first half, one at the end of the first half, and then one at the end of the second half. We see our trends match what the literature says. But we also found that d prime is maybe not the best thing to use because there's too few bursts of energy or speed in these games that we might not actually see our anaerobic capacity being fully utilized. This is still a work in progress. We're still coding it, but we would like to apply it in the future. So what are we seeing are our current challenges? Well, one, we don't know enough about the player other than their tracking data. We don't know if they are drinking Gatorade during and between halves, which would allow for more carbohydrates to come into the body. We don't know if they're taking different supplements like caffeine, which helps release more calcium, which allows for faster rates of contraction or more forceful rates of contraction, stuff like that. We don't know two things with changes in fitness. One, over the course of the game, your fitness decreases. This is partially due to cardiac drift, but this is also partially due to dehydration. So when we have, at the end of the game, we're seeing that heart rate has to go up to maintain the same pace of play. At about the 30-minute mark on, we see an increase in heart rate. We also see a decrease in blood plasma volume because of dehydration, meaning that the body now has to work harder to get more blood, or the same amount of blood and nutrients to the muscle themselves near the end of the game. We have a few others here, like personal profiling. Temperature, heat is a huge factor on central fatigue. Altitude being, if you can't take in as much oxygen, well, you're not going to be able to work as hard. And there's still issues with GPS data and IMU data being both noisy and somewhat inconsistent depending on the sample rate. So these are things we have to overcome to then apply to this. So first of all, I would like to apply the impulse response model. So this would be to understand how much fatigue is carrying over from the previous 2 or 3 weeks of practices in games to our player, for tomorrow, let's say. So we should be able to eventually estimate how much D prime or anaerobic capacity has been used before this. Are they coming in a somewhat not 100% or somewhat fatigued state already? I'd like to apply this to different sports, especially contact sports and more intermittent sports like hockey, rugby, basketball, and ringette. These sports expect you to give it your all for 20, 30, 40 seconds at the very least, meaning that you might end up seeing over time that D prime is being fully utilized between shifts, and should help coaches better plan for shift lengths and shift changes depending on how quickly somebody can reconstitute their energy. And the ultimate project, which is where I'd like this to end up going, is to track your opposition. If you can track who on the opposition is tired, you can track or you can understand how to attack that team. If their players on the left-hand side of the field are tired, you want to attack the left-hand side of the field. You also want to know that if your left-hand side of the field is tired, we'll push their attack to the right-hand side of the field. And this can all be estimated with video tracking and video analysis or analysis of your opposition. With all of that, this is a very brief overview of everything, but I want to thank you for taking time out of your day to watch this. I hope everything is going well and you're staying healthy and you're staying busy. If you have any questions, reach out to me via Twitter. That's probably the best way to go, and we can hopefully or potentially set up a video call at some point and go from there. Thank you very much.